but there's lots of examples of, I mean, they really went through and really vetted the STL in the latest one. So you can just pick up all kinds of things by looking at what they changed. But so there's a general problem. The next thing we'll talk about is invalidation problems. So containers implement value semantics, which means when you put something in a container, it makes a copy of what you put in it. You don't retain, you can't retain ownership of it. So basically, you put stuff into containers, but then you can pull out references, pointers, or iterators to them. Depending on the container, of course, there's certain semantics with different ones. So containers handle all the details for you, which means they do a lot of magic behind the scenes. In order to grow the data structure or manipulate it how you want, this can often involve moving their internal data structures around in memory. So there's a pretty well-known problem in C++ of invalidation, of iterator invalidation. And this is basically when the container invalidates your existing references. So how it would work is you have a container with a bunch of elements. You have a reference to something in that container. Then you do something to the container to cause it to move all its stuff around. Your reference pointer or iterator is now pointing at memory that it's basically, it's going to either be pointing at the wrong element in the container, it's going to be pointing arbitrary heap or arbitrary stack memory. Also, I put a couple of references to the CERT C++ secure coding standard, which you'll definitely want to check out. It's got a lot of good stuff. So we don't have time to really go through the different containers, but we'll look at vector really quickly because it's pretty simple. It's generally implemented as a dynamically allocated array. So you have, it's a buffer. You have an address, you have a size, and a capacity. The capacity is the number of elements it can hold, and the size is the number of elements it currently has. So right there, our buffer can hold 9 elements, but it only has 6. So if we added 4 more, it would have to grow its capacity. So that's called reallocation, and it's just like a C-realloc. The entire array can be moved, or the entire buffer can be moved in memory. So if the buffer is moved, any existing pointer, reference, or iterator we had to the elements would then be pointing at memory that would be pointing at the wrong memory, basically, because the whole data structure will be moved out from under us. So real quick, looking at the vectors in validation semantics, anytime you add elements or resize the vector in the growing direction, you can cause reallocation, which invalidates all of your existing references, pointers, or iterators. Obviously, if you think about how it works, it's just an array. So if you insert or delete in the middle, it's going to have to shift all the elements past the point of modification, either one over or one to the left. So necessarily, all of your references to those elements are then going to become invalid. They'll be pointing to the wrong element, or they'll be pointing outside the bounds of the container. And of course, anytime you insert an element, it can lead to reallocation. And then there's one final sort of obvious thing, is that if you have a reference to an element and you delete that element, your reference is no longer valid. So we'll look at a very simple example. So you can see we have a vector of records, and we read in the records from the network. And then we have an iterator pointing to the first element in the vector, which it's called ITR. Now, say we do some stuff, and later on we determine we need a termination record at the end of our vector. So we add this termination record at the end of the vector. And then we do some more stuff, and later on we say, okay, it's time to process our records, so we'll use that iterator. So the problem here is that the iterator is not necessarily valid because we modified the container during its life cycle. So most of the time, this probably wouldn't be an issue because there'd be room for the termination record. But if there happened to be no room for the termination record when it was added, the memory buffer would likely be reallocated, and the iterator would end up pointing at unused memory. Basically, it depends if something was allocated in the iterum or not. So looking at the invalidation semantics for the other containers, DEC's kind of interesting because it has pretty nuanced semantics. Basically, the DEC is it's kind of like a fancy vector. Basically, it's implemented so that you can manipulate either end of the data structure. That's the optimized use case, and it works by it has a bank of arrays. So if you insert in the delete in the middle, just like with a vector, you invalidate all existing references, pointers, or iterators. But what's kind of interesting is if you insert at either end, you invalidate existing iterators, but not pointers or references. And the reason this happens is because the iterators are smart. They have information about the internal data structures. So basically, the iterator will still seem to work. You can dereference it and get to the element, but if you use the invalid iterator and start walking it forward or backward, it's going to walk off into random memory because it no longer knows the correct internal layout of the deck. So list, map, multi-map, set, and multi-set, these have the most forgiving invalidation semantics because basically these are typically implemented as doubly linked lists or binary trees. So the nodes don't ever move. It's just the linkages that are moved. So the real risk here is, or the only risk really with these as far as invalidation is to have an iterator to an element, delete the element, and then keep trying to use the iterator. So basically, when auditing for iterator invalidation, there's kind of three patterns you want to look for. The first is mutation during iteration. So it's a pretty common construct to iterate over the elements in a container. So what you want to look for is is there any function called, or you have to follow the whole chain of control flow, but is there any way that the underlying container can be mutated during the course of this iteration? The second pattern is very similar. Basically, if you have to look at the life cycle of any reference pointer or iterator to an element within a container and determine if there can be mutation during that life cycle. And then the third pattern you want to look for is logic problems leading to deletion of unintended elements. So here's kind of a simple example of what mutation during iteration will look like. We have this process record set function. It's going through the records and calling process record on each one. And then a process record, ... represents a lot of code that does various stuff, but you can see that if one of the records happens to indicate that there's an exception record, then it goes back and it modifies the base container, which, as you know, can invalidate the iterator that's being used to iterate over the container. So we'll look at look at some logic problems with deletion. The first one is kind of like the canonical delete mistake. This is something probably everyone makes when writing STL code for the first time, but it's not likely to show up in code necessarily as a vulnerability. But basically, the problem here is that you actually erase the iterator that you're using, so it's invalid, and then you go try to increment it. And you'll see a lot of posts if you kind of research this of a lot of people like, why does my program crash? But it can manifest itself in more subtle ways in real code. I think we're running a little bit short on time. But basically the point of this example is that each element can specify another element that should be deleted, and there's a logic problem in that you can have an element that deletes itself, and then the iterator is invalid. So what's interesting is Microsoft's newest STL does a lot of security checking on iterators, and to some extent it prevents iterator invalidation because it does bounds checking of the elements against the container bounds. So for the most part it works. We found a couple of cases a couple of corner cases where if there was invalidation it wouldn't catch it. Like this is the vector iterator increment operator. And you can see that it checks to make sure it doesn't walk past the end of the container by checking if make sure my pointer is less than the last element in the container. This works good for a normal use case, but if the iterator was invalidated and the entire container was moved forward in memory, you can see that this check still passes because they don't check to make sure it's above the beginning of the container. So the next kind of problem to look out for are problems with ranges. So ranges are a common idiom in STL programming. A range is defined by two iterators, beginning and end. And a range is considered to be half open. And this means that the end element is included. So the things to look out for are situations where you can have a begin iterator after the end iterator. And this usually is going to result, basically this specifies a ridiculously huge range. And it usually results in memory exhaustion or an infinite memory copy. It depends on what's actually in your containers and what the template specialization magic turns it into in the end as to what kind of memory corruption you get. Another thing to look out for is begin and end in different containers. Obviously, that would be a pretty significant mistake. So begin or end outside of the valid range of container. Since if you're not using a checked STL, you can walk iterators outside. You can walk iterators past the bounds of the containers. This becomes a risk, and also because in certain situations, pointers and iterators are kind of function equivalently with certain containers. And then the final pattern to look out for when auditing is a source range bigger than the destination range. The copy algorithm, for instance, has 3 arguments. It has a beginning, an end, and a destination. So it doesn't actually have a destination. It doesn't have an end for the destination. So if you're using it like an insert iterator, it's not a problem. But in certain situations, you can get yourself into trouble by simply writing more data than there's room for. So here's a couple quick examples. The first example, we have an iterator, I1, and we're using the find algorithm to find the first an item we consider to be the first item. And then we have an iterator I2. We're using the find algorithm to consider the item we consider to be the second item. And then we use that to define a range, and we copy from that into somewhere else. There's a logic problem here, which is pretty straightforward, is that if the second item is before the first item, we have an invalid range. And that would basically make standard copy go crazy. Example 2, basically we fixed the first problem, but you see there's kind of an arbitrary increment of the second iterator, and if the second item happens to be at the end of the container, it's going to walk past the bounds of the container, and this could end up having standard copy writing more elements than NuVec had room for. So the final kind of pattern to look for are boundary problems. So iterators can be walked out of bounds unless you're using a secure STL, and these result in vulnerabilities similar to C-style array issues. And as you can see, they also facilitate the range problems we talked about. Also, certain containers have direct access operators, like subscript operator, and by the spec, they don't provide bounds checking, so you can you can easily run into trouble there. For vector, the vector and deck, I believe, the add operator by the spec does require bounds checking. And Microsoft's STL, the latest one, just does bound checking for both. Also, the front and back are container member functions that give you direct access to elements, and if the container is empty, then you run into trouble. And there's some kind of idiosyncrasies of some of the implementations, like G++ vectors pop back. If the vector happens to be empty when you call that, popback's supposed to delete the last element in the vector. Then it kind of screws up the internal invariance in the internal data structures, and following actions generally cause memory corruption of varying kinds. Some are controlled. And same kind of thing happens if you try to, for instance, if you erase with a position that's outside the bounds of the container. And we have a couple quick examples of those. Example 1 is like your basic keys to the kingdom kind of example, just to show that the subscript operator of a vector doesn't do bounds checking. So that would basically let you write anything anywhere. The second example, the point of that is that this EOS element that we're looking for, if that happened to be the first element in the container, we would call erase on an invalid position in the container, because we would call 1 behind the container. And in the third example, if read elements doesn't read any elements and my vec is empty, if we call popback on an empty vector, then the call to reserve is going to end up copying like 20K over the internal data structures.
Okay, the last thing we really wanted to cover here was